Okay, let's talk about the periodic table. I know, it looks super intimidating, right? Just a huge, complicated chart. But what if I told you it's not a chart at all? It's a map. A map to a perfectly organized city of all the elements in the universe. And today, we're going to hand you the keys to that city so you can navigate it like an absolute pro.
So, here's our game plan for this little tour. We'll start with the ultimate cheat sheet. Then, we'll get into the rows, columns, and families. After that, we'll uncover some periodic trends. We'll wrap it up with the big picture. And then, a little quiz to see if you're a pro. Let's get to it.
First up, the ultimate cheat sheet, laying down the law. You know, every city that works has a fundamental law, right? Well, the City of Elements is no different. So before we start wandering around, we gotta understand the one single rule that makes this whole thing make sense.
Okay, so the modern periodic law says the physical and chemical properties of elements are the periodic functions of their atomic number. Sounds kind of fancy, right? But honestly, it's super simple. All it means is that if you arrange the elements by their atomic number, that's just the number of protons they have, you'll see their properties start to repeat in these predictable regular patterns. It's this awesome rhythm, this repeating pattern, that lets us build the map in the first place.
All right, section 2, rows, columns, and families, navigating the city grid. Now that we know the law of the land, let's get a feel for the layout. Just imagine a city grid. You've got your horizontal streets and your vertical neighborhoods, and each one has its own special vibe.
So here's the breakdown. Those horizontal rows, we call them periods. They're like the streets of our city. There are 7 of them, and as you go down from one street to the next, you're adding a whole new electron shell to the atoms. Then you've got the vertical columns. Those are the groups. Think of these as neighborhoods. And what's cool is that all the elements living in the same neighborhood, they act in really similar ways. They're like family. So you might be asking, why do they act so much alike in the same group? Well, it all boils down to one thing. They're valence electrons. Those are just the electrons in the very outermost shell of the atom. See, every single element in the same group has the exact same number of these valence electrons, and that number is what decides how they're going to react and interact with everyone else.
And of course, some of these neighborhoods are so well known they've got their own special family names. Over in Group 1, you've got the alkali metals. These guys are seriously reactive. Then, way over in Group 17, you have the halogens, who are also super reactive, but in a totally different way. And then there's Group 18, the noble gases. They're the cool, aloof celebrities of the element city. They don't react with anybody.
And that difference in valence electrons creates this really cool dynamic. I mean, look at this. On one side of town, in Group 1, you have the alkali metals. They've got just one lonely valence electron, and they are dying to get rid of it. But then, all the way across town in Group 17, you find the halogens. They have 7 valence electrons, and they just need one more to feel complete. So they're desperate to snatch an electron from somewhere. It basically creates a whole city of givers and takers.
Okay, part 3, uncovering periodic trends, the rules of the city. So we've got the layout down. Now it's time for the really fun part, uncovering the city's hidden rules. We call these periodic trends, and they're just predictable changes you see as you move across a street or down a neighborhood.
First up, let's talk about atomic size, or atomic radius. The easiest way to think about this, it's the size of each element's property or house in our city. It's just the distance from the very center of the atom, the nucleus, all the way out to its outermost shell of electrons.
Okay, so here's the rule of thumb. As you go down a group, the atomic size gets bigger. That makes sense, right? But here's the weird part. As you go across a period, from left to right, the atomic size actually gets smaller. Yeah, you heard me right. The houses shrink as you walk along the street. How is that possible? Well, let's break it down. Going down a group is pretty straightforward. Each step down, you're adding a whole new electron shell. It's like adding another floor to a building. Of course, it's going to get bigger. But going across a period is different. You're not adding new shells, but you are adding more protons to the center. That makes the nucleus more positively charged. And that stronger positive charge pulls all those negative electrons in tighter, kind of like a stronger magnet. And that's what shrinks the atom.
All right, our next trend is metallic character. What does it mean for something to be metallic? Well, in chemistry, it really comes down to one thing: how easily an atom is willing to lose its electrons. The more willing it is to give them away, the more metallic it is.
So where do the most metallic elements live on our map? Well, the trend is this. Metallic character increases as you go down a group, and it decreases as you go across a period from left to right. So if you want to find the most metallic element of all, where would you look? Yep, the bottom left corner. That's where you'll find the king of all metals. Last big trend for today, ionization potential. This sounds complicated, but it's not. If metallic character is about how willing an atom is to lose an electron, ionization potential is the price you have to pay to take it. It's the amount of energy it costs to literally pull one electron away.
And this trend makes perfect sense if you think about it. As you go down a group, what happens? The atoms get bigger. That outermost electron is way far away from the nucleus, so it's easier to grab, right? The price goes down. But as you go across a period, the atoms are getting smaller, and that nuclear charge is getting stronger, holding those electrons super tight. So trying to remove one, it's going to cost you. The price goes way up.
Okay, Section 4, the big picture, your trends summary. We've gone through the layout, we've looked at the rules. Now let's zoom out and put it all together into one simple master cheat sheet.
And here it is. This is it, the master key to the whole map. We've already talked about atomic size, metallic character, and ionization energy. You'll see a few others on here too, but don't get bogged down in the details. Just look at the overall pattern. If you can remember that things get more metallic as you go down and to the left, and more non-metallic as you go up and to the right, you've basically cracked the code. All right, last section. Are you a pro? Time to test your knowledge. You've had the grand tour, you have the master cheat sheet. Think you've got it? Let's find out with a few quick questions. You ready?
First question for you. Which element has a bigger atomic size? Sodium, that's Na, or chlorine, Cl? Now, they're both in period 3, so they live on the same street. So think back. As you walk from left to right along a street, what happens to the size of the houses? Next one. Let's say you're moving down Group 1, the alkali metals. Does their metallic character, their willingness to lose an electron, increase or does it decrease?
And for the last one in our quick-fire round, which element has a higher ionization potential? Lithium, Li, or fluorine, F? They're both in period 2, so which one costs more energy to steal an electron from? Which one is holding on to its electrons more tightly?
Okay, and for a final big picture thought, remember how I said this was a map? Well, it's not just a map of what we know. It's a map that can predict the future. The table looks pretty full, but scientists are still creating new super heavy elements in labs. So here's the ultimate test. Where would you put element 119? And, using the trends we just talked about, what could you guess about its properties? Would it be big or small, a metal or a non-metal, super reactive? That predictive power, that's the real magic of the periodic table.